So when we talk about latent heat or hidden heat, this is a really important idea when we're talking about phase changes. So if we have a substance, let's say like a pot of water, and this water's inside, and we heat it up, there's a point at which it gets to the boiling point, and at sea level, that's 100 degrees Celsius. Now, if you put a thermometer inside, the water, even after you keep heating it, the temperature doesn't increase. It just stays at 100 degrees Celsius. But what happens is these particles, evaporate into the atmosphere, and well, not evaporate, but really boil into the atmosphere. You have some of that, you have evaporation too, but the molecules themselves break apart from the liquid, right? So that heat is actually going in and breaking those bonds. When you freeze something or melt something, right? If you have ice and you have heat coming into it, those bonds have to be broken, and then then you have a puddle of water. And it turns out both of these will be 0 degrees Celsius the whole time, until it all becomes water. So you're putting heat into this, and the ice cube is melting the water. You have there, and both will stay at 0 degrees because that temperature or that heat is actually breaking those bonds in there. So this is the key idea here with phase changes on the molecular level. The heat added is changing the state, and it does not increase the average kinetic energy of the molecules, and that's really important because the average kinetic energy of those molecules is the temperature, right? So what it does is we have those breaking those close bonds that are broken, and then the next phase can occur, and so the molecules are breaking apart, and we see that there. So temperature stays the same in a phase change, and it's really important to see that. I've got a time-lapse video that I show in class of an ice cube melting there, and it stays the same temperature the whole time. So the energy required for material to change, is latent heat again. And when we take a look at, the graph here, this is a really, really important graph looking at the phase changes and really temperature changes of water. So let's say you have water at 0 degree or negative 40 degrees, right? So you have an ice cube at negative 40. Now, if you put heat into this ice cube, if you look at the graph, right, it's going to increase in its temperature, negative 20, and then up to 0. And it's going to take a certain amount of energy to do that. In this case, 20 kilocalories. So this is based on, that scale. Once it's at 0 degrees, though, and if you keep putting heat into it, it's going to start to melt, and it's going to start to be an ice cube and water. And in this case here, this gap to here is 80, so 80 kilocalories, 80,000 calories for this, particular substance is going to melt it. Now, once you have melted water at 0 degrees, and you keep putting heat into it, in this case, 100,000 calories, in between 100 here to 200, then this water is going to increase up to water that is at 100. Now, once it's at 100 degrees and you keep putting heat into it, it's going to stay that same temperature, and you keep adding heat, all this heat, and this water will be turning into steam, and you'll have both at 100 degrees. So water and steam at 100 degrees. And then if you still have all that steam contained and you keep heating it, then that steam is going to increase in temperature. But if you notice on this graph, right, these straight lines, you stay at 100 degrees during that phase change. You stay at 0 degrees with water and ice. And so it's important to see that, during that phase change, it's those molecular bonds that are being broken. Now, we could also go the other way, right? We could also go, from a colder situation to a hotter situation. So, let's say we're coming this way, right? If you have steam at 100, or where's the steam at 100? You have steam at 100, right? And you cool it, what's going to happen is water's going to form, and you're going to have water and steam, but they're still going to be at 100 degrees. So if you're cooling it, it'll still be at 100 degrees. Now, once you get it to this point, it's 100-degree water now, and if you keep cooling it, the temperature is going to drop down to 0, and then you have water at 0. Then if you keep cooling it, then you'll have water and ice at 0 degrees, and so on. So this is completely reversible here. Okay, so the latent heat of fusion is looking at the heat required to change a material from a solid to a liquid. So if we have the latent heat of fusion for water here, 3,000 or 333,000 joules per kilogram degrees Celsius, that would mean if we have a block of ice, and that ice is 1 kilogram of mass, and we put in this many joules, so we'll put in 333,000 joules. We heat this by that much. That will take that 1 kilogram of ice and turn it completely into water. Now, what we're assuming here is it's already at 0 degrees. It's already ready to go. We'll look at what happens if it's not ready to go yet. And so this is how we calculate how much heat's required. If we have a different amount, right, different amount of mass, we can use the same latent heat of fusion value here. So let's go ahead and try that here with L7. You can pause the clip and do this, and then when you're ready to check, you can hit play to continue. All right, so in this case, we only have half a kilogram of ice. We have the latent heat of fusion. Should get 166,500 joules as the energy required to melt the ice. Now, vaporization, this one is maybe a little bit easier to remember because this is vaporizing, right? Like from a liquid to a vapor, or if we're reversing, cooling, we're going from a vapor to a liquid. We're assuming that our water is ready and it's already at the boiling point. So this is taking water that is already 100 degrees, and we have 1 kilogram of it, right? It's going to take this many kilograms, this many joules, 2,260,000 joules to be able to turn that into steam. And that's a lot of energy. Here is the equation, Q equals M LV, mass in kilograms, latent heat of vaporization we have here. And so, we get how much energy it takes to turn it into a vapor. So here's a table of different values. I usually like to just concentrate on here on silver because that's kind of fun. If you get silver to its melting point, which is 961 degrees Celsius, it's going to take 88,000 joules to be able to take that 1 kilogram of silver and melt it, completely melt it. So 1 kilogram of silver, and it would take 88,000 joules. Now, it's interesting, the boiling point of this, if you had liquid silver, is 2,190 degrees, okay? If you could get it to that point, and you put 2,300,000 joules into it, you can make this actually vaporize, which would be pretty crazy. So as we were dealing with this one here, and so you can see all these other values, right? Oxygen, nitrogen, water, lead, and so on. Now, if we take a look at a pressure cooker, this allows the temperature to increase much higher than 100 degrees Celsius. So, if you have like a rice cooker or something like that, it actually is cooking at a much higher temperature than 100, because as the pressure increases, it allows the boiling point to increase as well. And so, the radiator in your car is another example. It's under pressure, and that fluid inside, as it goes through, is transferring heat from your radiator, through your radiator, and then cooling off your engine. And so, it's under high pressure. And in fact, if you finish, if you drive your car and then open the hood and you take the radiator cap off too quickly, you're releasing it to atmospheric pressure, normal atmospheric pressure, and it can actually boil at that point because you don't have that, it's not under that pressure anymore. And so if you're at altitude, it turns out, if you have less pressure on it, the boiling point is lower, and so you may be boiling water at 96 degrees or 95 degrees. So it may take a different amount of time to actually cook things at higher altitudes. Okay, so let's take a look at this situation where we have ice at -5 degrees Celsius, and we want to get it to steam at 125 degrees Celsius. Well, we know there's got to be multiple steps here because, we're going to be phase changing as well as increasing temperature. So if we have an ice cube at -5 and we're getting it up to 0 degrees, we have that here, and then the next step will be, once we get it to 0 degrees, we need to melt it. And then once we melt it, we can keep putting heat into it, going from 0 degrees to 100 degrees. And then once we have water at 100 degrees, we can phase change it. And then once we have, water or the water at steam at 100 degrees, then we can increase the temperature to 125. So I'm going to go ahead and we'll go ahead and set this first one up here. So, the heat required to get from -5 to 0 degrees, we have the mass 0.35 is the mass. We have the specific heat of ice, and then we have 0 minus -5. And so it'll take 3,675 joules to, get that to to 0 degrees. Now what I want you to do is calculate what is the energy needed to melt it. So this is fusion, latent heat of fusion. For this portion, the specific heat of water is 4186 joules per kilogram degrees Celsius. So you can figure out how much energy it takes to go from 0 degree water to 100 degree water. The next one is a phase change. So this is vaporization. And then the last one, we're going to increase the temperature Q equals MC delta T using steam. The specific heat of steam is 2010 joules per kilogram degrees Celsius. So go ahead and pause the clip and figure out these different ones along the way, and then you're going to add all of them together to get a total, and then that total will be the total amount of energy it takes to take this ice cube at -5 and then get it to water, or to steam rather.